Alright guys, we are talking about exponential functions, or specifically today we're talking about exponential growth. You should have studied exponential growth and decay pretty heavily before, but we're going to make sure that we really master these skills in this unit. There are so many applications of exponential functions in the real world. That's why it is so important. It's something that we definitely want to be able to understand the nature of what's happening in these functions. So let's talk about what exponential functions are. So exponential functions of base a, some constant a. It's f of x equals a to the x, where a must be greater than 0, but it's also not equal to 1, and x is any real number. So again, this fact right here, I don't know if it's a fact, it's part of the definition, is extremely important. It has to be greater than 0, which means it could be 0.5. It could be 0.362. It could also be 1,000, right? It has to be some number greater than 0, but it can't be 1. Why can't it be 1? Well, think about it. Actually, I ask you this question next. Why do we have these restrictions? Well, what would happen if a was 1? And what would happen if a was less than 1. So I want you guys to put me on pause right now. Think about that. Write something down. So if a was 1, we'd have a horizontal line. Think about that. A to the first power. For any number a, it would be y equals 1. So, that's just a horizontal line. That's not exponential growth. Or decay, I suppose. If a was less than 1, it wouldn't be continuous. If you don't know what I mean by that, go ahead and plug something in your calculator. Plug in negative 0.26 to the x power in your calculator and see what you get. Okay? You guys can experiment with that. So we have some properties of exponents that are going to be important for us to remember, especially with exponential functions. So what I'd like you guys to do is right now put me on pause and say what each of these equals. Again, we're just recalling these properties. So go ahead, put me on pause, and then we'll check. Let's quickly check our answers here. So we know if I have a to the x times a to the y, that's a to the x plus y, which is oftentimes confused with this guy down here. Okay, so if I have a power to a power, remember we multiply their powers. Okay, a to the x over a to the y, division of exponents, we can subtract their exponents. We also recall that if I have a negative exponent, that is 1 over a to the x, right, to get a positive exponent. Anything to the 0 power is 1. Anything to the first power is itself. Here, it's almost like we're distributing the exponent to both terms, a to the x, b to the x. We already talked about this one. Same thing here, a to the x over b to the x. And last but not least, if I have absolute value of the squared term, well, I know that if I'm squaring a term, it's always going to be positive anyway. So having the absolute value brackets is kind of redundant. Very good. Okay, next, what I'd like you guys to do is I want you to graph by hand both of these exponential functions, 2 to the x and 3 to the x. Okay, you can do that on the same coordinate plane here. Then once you're done, I'd like you to state the domain, range, and identify the asymptotes and intercepts of each f of x and g of x. So I'd like you guys to go ahead and put me on pause and do that. If you're not sure what to do or how to do this, just from the start, table values. All right, you've done this before, you can do it again. Here we go. So I graphed these two on the same grid here. Now what's in green here is the g of x, which is 3 to the x, and what's in blue here is f of x, which is 2 to the x. So you notice that they both have this same kind of curve shape, right? That's how it should be. These are exponential functions. What makes them exponential? Well, look at the growth over time. I should probably graph it. We do actually have a horizontal asymptote here at 0. So these graphs will approach 0 as we approach negative infinity in terms of x values, right? And then, as we increase our x values, notice what's going to happen to our y values. They grow exponentially. Now, just comparing f of x and g of x, which one grows exponentially faster? The one that's in green here, the one that is 3 to the x in comparison to 2 to the x. And then you guys were asked to state these characteristics. So you'll notice that both of them have the same domain, same range. Neither of them have x-intercepts because there's an asymptote there. They have the same y-intercept, and then they both have the same horizontal asymptote. So just some things to ponder as we move forward. All right, next one. So this is without graphing. So now just using our knowledge of transformations of graphs. How do g of x and h of x transform in comparison to f of x? So go ahead, put me on pause, and then we'll check our answers. For g of x, the key thing here is identifying like what's inside, quote unquote, inside of my function, what's outside. So this will go left 3 and down 7. Here I have 2 to the negative x. So you could have said one of two things. I'll probably use the types of descriptions where I say something like reflect over y-axis, which is the case here. Or if you said divide x values by -1, that also satisfies the same thing. Awesome. Okay, so we also have something with a natural base, meaning it was born to be a base. Ha ha ha. Okay, so we have this number e. You're like, what? That's a letter. Actually, it's a number. So e is part of our irrational family. It's probably the second most common constant. Do you know what the first most common constant is? That's irrational. Ding, 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 pi. Pi is, e's in the same family, okay? So we actually can calculate e. So let me show you how it is. Let me pause for a second. So I know you're thinking like, wow, this looks fun. Why didn't you let us do this on our own? Sorry, I'm just selfish. But anyway, this is how we actually calculate e. They do have the same work and description in the textbook, so if you're curious, go ahead and check it out. But we can actually calculate the value of e using summation notation and also limits, which we're going to spend a good chunk of time on coming up next semester. But all of these forms get us to really calculating that the value of e is 2.718. And so and so and so. And we know because it's irrational, it does repeat forever without having a common pattern. So the value of e is 2.718, kind of like how we know that pi is 3.14. I would know this as well, just for fun, to sound educated. So the natural exponential function is f of x equals e to the x, where e is the number e. It's not a variable. You don't plug things in, okay? Don't be silly. So let's evaluate for x equals 1.9. Okay, so let's find out what g of 1.9 is. So go ahead, try that on your own. FYI, you will need to use your calculator and round your answer. I'll show you when we come back where that is located on your calculator. Go ahead, put me on pause. G of 1.9, you should get that it is equal to negative 0.9036. How do I plug this into my calculator? Well, guys, here's my graphing calculator, which all of you bring to class every day. So the e, so here's pi, right above that caret sign. E's in blue above the division sign. So, for example, if I wanted to figure out what e is equal to, enter. Wow, cool. Anyway, also if I wanted to just put e to an exponent, I could use second and the natural log button, which we'll talk about soon. I could put, whatever exponent I wanted. It's pretty sweet. Cool, huh? Wonderful. All right, so making sure that we understand exponential functions that have a base of a, what are our restrictions and why, and also we could have a base of e, which is the natural exponential function. Okay, understanding the nature of exponential growth. What does that mean in terms of a graph, in terms of numbers, in terms of life? Good job.